Module 7 covers ICS Recon, pen testing, and vulnerability assessment. Upon completion of this lesson, students will be able to describe the purpose of ICS network reconnaissance, describe the common tools of ICS network reconnaissance, identify the ICS devices on a network, perform penetration testing on an ICS system, describe vulnerability assessment, VA, understand the common ICS vulnerabilities and the various VA techniques, perform a vulnerability assessment of an ICS system, understand the function of a network firewall, describe the categorizations of firewalls, and configure an ICS firewall. First, let's investigate ICS network reconnaissance. ICS network reconnaissance is the process of scanning the ICS network for the purpose of mapping the devices attached to the network and their vital statistics, such as ports opened and closed, IP addresses, services offered, and operating systems. Although this process seems to be passive and non-intrusive, it could have a harmful effect on an ICS. The most common and basic tools for network reconnaissance are ping, netstat, and traceroute. More advanced tools, which will be the main topic in this lesson, are the Nmap and the Zenmap network mapping tools. Ping. This is a command line network utility tool that comes with most operating systems. This tool sends out Internet Control Messaging Protocol, ICMP, echo packets to a specific host to check its responsiveness. However, if the firewall on the host is configured to block ICMP requests, it would appear that it is not responding to the request. In IPv6, the equivalent command is ping 6. Netstat. This is another command line network utility tool that is used to display network connectivity information, such as the contents of the routing table, the active ports, the number of bytes sent and received, and so on. Traceroute. Traceroute, TraceRT in Windows, is a command line network diagnostic tool that is used to determine the route to a specified host by sending Internet Control Message Protocol, ICMP, echo packets to that host. In these packets, traceroute uses varying time to live, TTL, values. The TTL value is 1 at the start, so when it comes to the first router, it is decremented to 0. The router then sends an ICMP time exceeded message back to the source. The TTL is incremented at each subsequent transmission until it reaches the specified host. This technique allows the source of each error message to be documented and hence tracing the route from the sender to the receiver. Nmap. Nmap Network Mapper is a free and open source utility for network discovery and security auditing. It uses raw IP packets to discover hosts on the network, the services offered by each of those hosts, the operating system running on each, the type of packet filters and firewall in each, and so on. It is available for all major operating systems such as Linux, Windows, and Mac OS X. ZenMap. ZenMap is the graphical interface of Nmap. It is still free and open source. ZenMap can arrange its display to show all ports on a host or all hosts running a particular service. It summarizes details about a single host or a complete scan in a convenient display. It even displays a map topology of discovered networks. Further, it facilitates the saving of previous and current scans for the purposes of comparison and establishing network and system baselines. Configure a small network similar to that shown on the figure. Download and install ZenMap on host A. Install and run OpenPLC runtime on host B. This can be done with virtual or physical machines. For example, you can set up VirtualBox OPA Windows system and a Kali VM and a Windows VM connected via a virtual network in the VirtualBox. Make sure that the OpenPLC web interface on host B is remotely accessible by browsing it from host A. If it is not accessible, enable HTTP service on port 8080 on the Windows firewall of host B. When remotely browsing the OpenPLC web interface from host A, the display web page should resemble the figure shown. Refer to the handouts for a complete instruction on how to install and run the OpenPLC editor and runtime. Next, double-click on the ZenMap icon to launch the GUI. You should see a user interface similar to that shown in the figure. Enter the target address, select Quick Scan on the drop-down profile, and click the Scan button. The output of the intense scan on all TCP ports is shown in the figure. This time, the Modbus TCP service is manifested, and port 502 is open for that service. The three major implementations of Modbus include Modbus Plus, a high-speed token passing network, asynchronous serial communication, and Modbus TCP, the TCP IP over Internet encapsulation. The Modbus protocol specifies the protocol data unit, PDU, which is comprised of the function code and the data field, and it is independent of the underlying communication layers. A summary of the most important function codes is shown in the table. Note that coils are 1-bit storage or output. Registers are word size. The Modbus organization, modbus.org, extended the Modbus protocol to work over the Transmission Control Protocol, TCP, by encapsulating the Modbus PDU with the Modbus TCP ADU. This protocol is registered to utilize port 502 and is realized by augmenting the standard Modbus PDU with the Modbus Application Protocol, MBAP header, as shown in the figure below. The MBAP header is made up of the following: a 2-octet transaction identifier, TID, a 2-octet protocol identifier, PID, a 2-octet total length, LIN, in bytes of the remaining fields, and an octet indicating the unit identifier, UID, which identifies the remote slave connected by a serial line. Here are the prominent ICS protocols and their standard assigned port numbers. Building automation and control networks, or BACnets, are predominantly for building automation such as HVAC, lighting, access control, and detection systems. DNP3 are most often used by energy companies. The figure depicts a Wireshark interface. The ICS packet capture name is ICS_packet3.pcapng. Note that source address, source port, destination address, and destination port. The destination port indicates a Modbus device. Packet 4 is a Modbus packet. Refer to the Modbus TCP ADU slide to understand the Modbus TCP segment of the packet. The Modbus segment contains the function code, value 16 indicates write multiple registers. The word count is equal to 6, indicating 6 values will be written to the output registers of the PLC. The values written starting at register 2 up to register 7 are shown. This is a sample laboratory project for ICS penetration testing using Metasploit. Number 1, install Docker on your system. Number 2, use Docker to install an image with Metasploit with the command docker pull strm/metasploit. Docker run -rm-it strm/metasploit. Use auxiliary/scanner/SCADA/Modbus client. Show options. Set rhost 192.168.1.225. Set data_coils 111.000.11. Set data_address 1. Set our port 502. Run. Here is another laboratory project for your students. The objective of this lab is to use ModPull to perform penetration testing on the control device found on an internal network, and to use Radzio Modbus Master Simulator for verification. Continue to the next slide. After unzipping the compressed file, you may run ModPull on the console. You may either use the Modbus RTU or the Modbus TCP protocols. When using the Modbus RTU protocol, specify the COM port of the TTY line. When using the Modbus TCP protocol, specify the IP address of the PLC device. Example runs are shown on the next slide. Here are some sample runs on using Module for pen testing. Make sure you use the correct IP address of the system you are doing the pen testing on. Here is a snapshot of a Module run. Note the correct usage of the Module and its output. The figure depicts the user interface for the RADZIO simulator. First, you need to specify a new project using File, then New. Second, you need to specify the connection settings by Connection Settings. You will then select the radio button, Modbus TCP, and set the IP address and port number. Refer to the settings shown in the figure. Click OK to set these parameters. For each of those Module sample runs shown in the previous slide, you should be able to see values displayed on the user interface. Now, let's look at ICS vulnerability assessment. Network scanning. This is also called network fingerprinting or network reconnaissance. The objective of this technique is to identify the network configuration and discover the connected devices in the network. Vulnerability scanning. This takes the information gathered during the network scan and performs a vulnerability scan on each of the devices for security weaknesses. Log review. A meticulous inspection of the system and security logs may reveal some vulnerabilities that may not be apparent with other techniques. Integrity checking. A review of the system files using checksums and hash signatures may reveal tampered files that could jeopardize the integrity of the system. Physical access review. Checking the access policy on the physically secured perimeter should also be part of the vulnerability assessment process. System access and authorization review. It is also imperative that a stringent access and authorization policy and enforcement mechanism be in place. The VA process must check for compliance by performing periodic and automated actions such as password cracking and auditing for access logs. Penetration testing. Using the results of the other techniques, penetration testing emulates the behavior of the attacker in trying to get unauthorized access into the system. The success of this technique essentially validates the associated vulnerabilities and requires immediate remediation. Common ICS software and product security weaknesses. The predominant sources of security issues that are found in this category are the lack of pervasiveness of security culture among developers and the deficiency of secure software design and coding practices. This category of security weaknesses includes the following: improper input validation, poor code quality, permissions, privileges, and access controls, improper authentication, insufficient verification of data authenticity, cryptographic issues, and credentials management. ICS software security configuration and maintenance development. Common ICS configuration weaknesses. This category is concerned with the manner in which the ICS equipment is installed, configured, and maintained. The lack of standard procedures in securely configuring ICS products and the great disparity of ICS vendors and products contribute to the persistence of this issue. These security weaknesses are due to the ICS installation, configuration, or maintenance errors that are enumerated below. Permissions, privileges, and access control. Improper authentication. Credentials management. ICS security configuration and maintenance. Planning, policy, and procedures. And finally, audit and accountability. Common ICS network security weaknesses. It is imperative that the ICS network architecture, in conjunction with the entire enterprise network, be securely designed through segmentation and segregation, a defense-in-depth mechanism. By segmenting the network into security zones and controlling the flow of information between these zones, security risk can be minimized. The secure ICS architecture concept is explored in more detail in a subsequent lesson. This category of security weaknesses includes the following. Common ICS network design weaknesses, which includes the lack of security perimeter definition, the lack of network segmentation and DMZs, the non-existent firewalls, and the bypassing of firewalls. Weak firewall rules, ICS network component configuration vulnerabilities, which include network devices not securely configured and port security not implemented. Audit and accountability, which includes the issue of a network architecture that is not well understood, the weak enforcement of remote login, and the poor monitoring of intrusion detection systems. Network architecture not well understood. Weak enforcement of remote access. And poorly monitoring of intrusion detection systems. OpenPLC, as described in the previous module, is an open source software that is designed and implemented to emulate a physical programmable logic controller. NUSIS is one of the most prominent vulnerability scanners currently available on the security market. We will be using the trial version of this software in the following section, but the professional version is capable of security auditing industrial control system, SCADA system, and embedded system applications. Both of these software tools are capable of running in various operating systems. In the previous lesson, we have shown OpenPLC running on a Windows platform. In the following exercise, we will be using OpenPLC and NUSIS on a Debian-based Linux system. NUSIS is the vulnerability scanner that will be used to scan the OpenPLC server. You first need to register the NUSIS home at https://www.tenable.com/products/nusis-home. You will then be provided a link to download and install the NUSIS client. You should receive an activation code in the email you used to register. After Nessus is installed, open a web browser and navigate to https://localhost:8834. When prompted, enter the activation code, create a new user account, and wait for the installation to complete. Once you have finished, you will see the Nessus Scans dashboard. Create and configure a scan for OpenPLC. Begin by clicking the New Scan button. On the next page, select Basic Scan. Here, enter the following parameters for the new scan. Name the scan something such as OpenPLC Basic Scan. If you are not running OpenPLC on the same computer as Nessus, you will need to enter the computer's IP address in the Targets field. Otherwise, enter 127.0.0.1 for the localhost address. The other settings can be left at their defaults. Click Save to create the scan. On the Scans page, click the Play button to launch the scanner. This will scan all the common ports on the target, including port 502, used by OpenPLC for Modbus/TCP traffic, and port 8080, used to configure OpenPLC from a web browser. This may take a few minutes to complete. Once the scan is finished, click on the scan name and then click on the host running OpenPLC. A list of vulnerabilities should appear. You should notice 3 detections in particular, listed as SCADA in the family column as shown in the figure below. By clicking on a specific vulnerability, a detailed description of that vulnerability will be displayed. In summary, an attacker of an ICS, here simulated by an OpenPLC server, could potentially read the discrete inputs, read or write to the coils, or obtain the device's slave ID. All of the above could be accomplished without an attacker providing any form of authentication. These actions are part of the pen testing activities. In this section, we will closely look at ICS firewalls. The concept of a firewall originated from the wall that separates sections of a building, having the purpose of preventing fire from spreading from one section to another. In network security, a firewall is a device that determines whether to allow or to discard a packet that goes through it depending on certain preset policies. Whitman and Matford provide a categorization of firewalls as follows. Packet filtering firewalls. These are network devices that examine each incoming and outgoing packet for information that are allowed or disallowed by the preset rules. These pieces of information may include IP addresses, port numbers, packet types, service types, flag settings, or protocol types. Application layer proxy firewalls. As the name implies, this firewall works on the application layer of the network hierarchy. It provides both proxy and firewall services. While a firewall service provides for packet filtering, a proxy service provides for an interface between the requester of information and the server. The drawback of using an application layer proxy firewall is that they are designed for a specific application layer protocol, and it is very difficult to reconfigure for other protocols. Stateful packet inspection firewalls. Using a state table, this firewall keeps track of the established network communication between two endpoint systems. The state table contains the information about the state and context of each network traffic. It is stricter than a simple packet filtering firewall in that it restricts access to packets that are essentially responses to internal requests. However, this extra work of verifying packets against the state table can be overwhelming in the face of excessive incoming external packets. Unified Threat Management, UTM devices. This device is a conglomeration of various network devices. It functions as a stateful pack inspection firewall, an intrusion detection and prevention system, a spam filter, and malware filtering system. A more advanced version of this device could also be configured to work as a deep packet inspection DPI system. Next generation firewalls, NGFW. This type of firewall works essentially like the UTM devices with the ability to do decryption of encrypted packets. There is very little difference between the two, but they maintain the same disadvantages of having all security functionalities concentrated in one device, a single point of failure.
Firewall IP tables. IP tables are a command line utility that are used for configuring a software-based firewall in Linux. They use policy chains to allow or block traffic. When a connection attempt is made on a system, IP tables look in its list for a rule to match the connection request. A no-match result forces the firewall to default action. IP tables can easily inspect the headers of network and transport layers and is made up part of the popular Linux distributions since the 2.6 kernel. IP tables are a collection of tables. The default table is the filter table. The other important tables are the NAT and the mangle tables. A table is a collection of chains. A chain is a collection of rules. Each rule defines a criterion or criteria and a target. A matched criterion or criteria moves the process to the rules specified in the target or executes the target value. If the matching is unsuccessful, the process moves to the next rule in the chain. The figure below illustrates the IP table's structure. The default filter table uses the following three chains. Input. This chain is used to control incoming connection packets. Forward. This chain is used to control incoming connection packets that are not to be delivered locally. The chain is used mainly for packet forwarding. Output. This chain is used for outgoing connection packets. Within this chain are rules regarding the decision to deny or to allow outgoing packets. Target values. Target values can be one of the following. Accept. The firewall will accept the packet. Drop. The firewall will drop the packet. Queue. The firewall will pass the packet to the user space. Return. The firewall will stop executing the next set of rules in the current chain for this packet and will return control to the calling chain. Notable advanced features of IP tables are string matching support and the U32 match. The U32 match allows the extraction of 32 bits of packet data from a specified location and the comparison of the extracted 32-bit information with a specific value. Using the header length information of the variable IP and TCP headers respectively, the U32 utility facilitates the movement to the beginning of the ICS payload. The following algorithm, due to Nevathan and Papa, illustrates this process. Number 1, extract the header length field from the IP header and multiply it by 4 to get the header length in bytes. Use this value to jump to the beginning of the TCP header. Number 2, extract the header length field from the TCP header and multiply it by 4 to get the header length in bytes. Use this value to jump to the beginning of the ICS payload. Number 3, specify an offset with respect to the beginning of the ICS payload and compare it with a specific value. The following rule illustrates that dropping a packet that contains a payload to read the identification of a Modbus device, function code 43. The -M option specifies the U32 feature. The --D port option specifies the Modbus port 502. The header length field for IP is bits 4 through 7 of the first byte of the header. Applying U32 will yield the first 32 bits, and right shifting by 22 bits will yield the length multiplied by 4. The value is extracted by masking the result with 0 by 3C. Finally, the @ symbol indicates a jump ahead by the number of bytes as indicated in the preceding expression. At this point, the current packet position is at the start of the TCP header. With U32, the next 32 bits is extracted starting from the 12th byte position at the TCP header. This is multiplied by 4 by right shifting 26 bits and applying the mask 0 by 3C. The @ symbol indicates a jump ahead by the number of bytes as indicated in the preceding expression. At this point, the current packet position is at the start of the Modbus Application Protocol MBAP header. The Modbus function code 1 byte follows the 7 byte MBAP header. Thus, starting at the 7th byte position extract 32 bits, right shift those bits by 24-bit positions, and masking those 8 bits with 0 by FF will yield the function code. This value will be compared with 0 by 2B, 43 decimal, which is the function code for Modbus device identification. The -J option specifies the dropping of the packet.